Okay, so if you're watching this now, we started a little late because I forgot to hit record. There'll be one of these temperature ones on the test. I forget if I put two on there. This one's saying highest temperature recorded, whatever at UH, the athletic field was 122 Fahrenheit, express this in Kelvin. So there's no way to go from Fahrenheit straight to Kelvin. You've got to go from Fahrenheit to Celsius. That's this equation here, which you can see up at the top. So I've mentioned it before, but I try to minimize the amount of memorization, especially for an in-person class, but for here as well. Is you'll have plenty of testing on your memorization capabilities in all your other classes. In chemistry, it really is about, for the most part, it's usually doing math to chemical situations for 161 and 162. Anyway. Okay, so you got to get from fluorine, you got to get from Fahrenheit to chlorine, to Celsius. Wow, I got that last problem on the brain. And that's this equation, right? The scale between these two, Celsius and Fahrenheit, were off by 32, the 0 point. So that 0 point does that adjustment. And then the 9/5 is the size of the units. And we get to our temperature, then you just, and Celsius, then you just add the 273 to it. And the 0.2 is because technically it's absolute zero. The Kelvin scale is 273.15. But that's a minor detail. And you'll see like this on the test, right? I'm not trying to trick anybody. These are, this is real similar to what you'll see on the exam. If it's some number, numerical answer, I'm not going to put 323.1, 323.3. I'm not trying to trick people by rounding. So if the number you get on your calculator is extremely close, then that's the right number. 6 is another one that's right. This is too easy. This is that polyatomic ion sheet. And when it's an in-person class, we do stress that you have those memorized because you're going to use them the rest of the semester, the rest of the year. For 162, you'll see them again. If you're a bio major, you'll see these things in OChem as well. So it's important for especially for those people, you're going to use these all year long. It's a little too silly, obviously, to have them here on a test because you can just have the sheet taped up on the wall. 7, this is a good example. There's 2 or 3 of these where this math is extremely simple if you know where the numbers come from. So 7 asking you how many neutrons does vanadium-51 have. So this is a good one where there's obviously no rounding, right? These are whole, either you have the proton or not. So it'll be a fill in the blank one, not a multiple choice. And there's 2, maybe 3 of these. So the mass comes from the protons and the neutrons. The number next to the element is the mass. So you're just going to the periodic table, finding where vanadium is. It's the 23rd element. Subtract that from the total mass, and that gives you the number of protons. 8's a little too simple, for an online type of test, with open book type of test. But this is just asking you, making sure you have the concept of the modern view of the atom, where protons and neutrons are in the nucleus and the electrons are circling around outside. So it's important because we'll come to chapters here, and a few chapters, where the shapes and the movement of these electrons become important. So you have to know where they are and that they're not in the nucleus. 9 is a balancing one. There'll definitely be a balancing one on here. This is a pretty simple hydrocarbon, or smaller hydrocarbon, C4H6. Combustion completely with O2 gives us carbon dioxide and water. It doesn't matter whether you start with carbon or whether you start with hydrogen, right? And that's because it's in one species on the reactant side, and then on the product side, it's the carbon and the hydrogen are both in one species. The oxygen you always, in any element, but in these combustion ones, the oxygen you should always leave for last because it's in three things. Anytime they're in more than, if they're in three or more, you want to leave that element for last. All right, so 4 in front of the CO2 because there's a 4 on our hydrocarbon to start with. So now we know that that coefficient is going to be 4 or some multiple of 4. I mean, you can already see the answer down there, but so 4, 8, 12, 16, something like that. All right, we got 6 hydrogens on the reactant side, so we'll need a 3 over on the product side. And 3 times 2 is 6, right? So we know it's going to be some multiple of 3. I mean, you can see the answer, but 3, 6, 9, etc. Okay, so then oxygen is left to do. And basically the way this works out is since there's a 2 here for the CO2, that's always even. It's really what this integer, if it's odd, then you're going to have an odd number of oxygens. That means the matching amount coefficient is, in here, 11 halves. You can't have a half a molecule of O2, so then we need to multiply the whole reaction by 2. So there's definitely one of these combustion ones on the test. 10, which of the following is a nonmetal? There might be one that simple like this on the test. This is reading the periodic table and understanding where it is. So, you'd during an in-person test, you'd be given the periodic table as well. So this is making sure that you've looked and seen it all and know metals, nonmetals, metalloids, etc. 11 is another one of our isotopes, right? Protons and neutrons. And if you look, let me pull it up. Periodic table that we've been using. So it's talking about the only, radioactive elements, lightest of all, is 43 protons. That's this element called TC, and it's used in medical diagnostics. So this doesn't exist on Earth. It's radioactive and it's decayed away. So it was here whenever the Earth was first formed, but it's radioactive, so it's decayed away and there's none of it left. And the way they make it is you take an element next to it on the periodic table, like I think the molybdenum. Let me change the share. So you take the element right next to it and you bombard it in a nuclear reactor, and then you make this technetium. So the way these work is with pneumatic tubes, which I don't know if anybody's ever seen this. I mean, you don't see them too much anymore, unless you're in. Now everybody emails things and whatnot, but the way I used to see it was when I was a kid, there was a drive-through at the bank, and you would put your check or whatever and money, etc., in a tube, and then there would be a vacuum created, and there was a little like flashlight-sized thing, cylinder-looking thing that you put in the tube, and it shot up over to the teller. You didn't pull up next to them like at a drive-through where they actually hand you food. So they would take the check, cash it, whatever, put the money back in and shoot it over to you. And in really large office buildings, like New York City type thing, if you had a document you wanted to get filled out and signed, you put it in these tubes, right? And obviously going down, gravity does the work, but to send it up, they would use vacuums. And so kind of like the way as how a gun works is the gunpowder explodes and you have a huge pressure behind it. The vacuum does the same thing, but it creates a suction in front of it and lifts it up. Basically, you suck, soda or whatever out of through a straw and into your mouth. Anyway, that's how they load up. They have those same tubes for this this molybdenum that they shoot into the nuclear reactor. You leave it there for a controlled amount of time. then you can make technetium. Then this gets used in lots of different imaging, breast cancer and all kinds of things, because it has unique properties, some of which we'll see when we start to talk about the behavior of electrons. So the elements that have a white lettering or just the black outline are radioactive. So this one, technetium, is the highest in the table, right? 43. The next closest one is this one, 61, called promethium. And you can tell this was, discovered more recently, being technical, or technetium being the name of it, right? And then here's all the classic synthetic ones that didn't exist on Earth, and they have these names, that were discovered pre kind of World War II, that have to do with atomic energy and weapons and whatnot, americonium, berkelium, etc. All right, so back to here. 43, you go to the periodic table, you find that that's Tc, so that eliminates answer B. And D, E, this is subscript, and it should be superscript. It's 43, that's just the protons, it's obviously not the mass, so that doesn't make sense. It told you the mass here is 99, so that should be up top, so it's in the right place on D, but this looks to be 99 plus 43, so that's doubling the protons and the neutrons, and so A is the only one that's correct. 12 here is another balancing one, another hydrocarbon one. We don't really care what it is. This one's octane, and this is where the octane rating. So when you go to the gas station, you'll see different prices for different gasoline, and it's called an octane rating. And ironically, what this molecule, octane, has a rating of 0. And the reason for that is the C8 here is in a straight line, and it turns out when you have in a carbon sense, this would look like, I don't know, 8 inches of rope. Whereas what's really more beneficial for a car is internal combustion, is if it's branched. And so if it looks, let's say you had 4 carbons in a row, and then 1 and 2 carbon branches off it, give you a much higher octane rating. Anyway, so I chose here to do carbon again first, but it doesn't really matter which you do, right? There's 8 carbons in the hydrocarbon, so we need 8 CO2s, or we're going to have some multiple, right? So you leave the 8 there knowing that it's going to be that, either stay as 8 or it's going to be 16, 24, 32, some multiple of 8. All right, could have done hydrogen first, doesn't matter which. I did it second. There's 18 on one side, there's 2 hydrogens and CO2, so we need a 9. Here's that odd number again. So 16 plus 9 is 25. We know we need 25 oxygens over here. It comes as O2, so we divide that number by 2, so it would be 12 and a half. You can't have 12 and a half, so we need to multiply the whole reaction by 2. So 2, 25, 16, 18. 13, I think I put one of these acid ones on here, some acid question with names and formulas, which you could either look up, but if you know it, then it's, it's quick. I had to put in problems that weren't, straight memorization that you could just look up, but a little detective work, or a little, if you caught it, read the book, saw it in the slides type of thing. Okay, which of the following is polyprotic? So when we covered acids, right, anything that starts with an H in the formula is an acid, which all of these are, except for obviously D, the answer there. And polys means many. The element hydrogen is 1 proton, and we talked about the uneven splitting of water. What makes something an acid is it's H plus. Then all 3 of these, A, B, and C, are those polyatomic ions where they were just an item, a species there to bring the negative charge to counterbalance the H plus or the proton. So poly meaning many, protic meaning H pluses, and acid, since it starts with an H in the formula and delivers. So D is the obvious it's not even an acid, let alone poly. So 14 is another temperature one. It's talking about oxygen gas, giving us the temperature that it boils at. So the Fahrenheit and the Celsius scales both have negative numbers, which is why we don't use them in the chapter on gases that we'll get to. I forget if that's next or 2 chapters ahead. Anyway, the point of it is we'll do some math and we'll have a formula called the ideal gas law. And you can't have negative numbers in it because the temperature is related to the volume and the number of moles, etc. And you can't have a negative volume or a negative number of moles. The amount of gas you can be talking about or analyzing is like your age. It starts at 0. So we need the Kelvin scale for all of our work with gases coming up in a chapter. So, all right, so like before from Fahrenheit, the 32 corrects for the different 0 points, the 9 to 5, 9/5 corrects for the size of the degrees. And so that gets us to our temperature in Celsius. And then all you do is just add 273 to that. 15, a little too easy maybe for an exam. There are a few easy ones on there, but this is just going to all the solutions that we talked about and the math behind. What makes something a solution is you have 2 things mixed together, the solute and the solvent. The solute, in general for us, especially if you're in lab, is usually going to be sugar or salt or something like that. But technically, if you think about the air we breathe, it's a solution where oxygen gas is about 20%. So it would be the solute, and the nitrogen gas is about 80, and it would be the solvent. Determine the percent yield of a reaction that produces 28.65 grams of iron when 50 grams of iron oxide with excess aluminum. So this isn't a limiting reagent since it's telling you excess. So what we want to do is take the grams of iron via the mass, the iron oxide via the mass on the periodic table, and get to those moles. That'll tell us what the theory is, and then we divide the amount they told us that was found by the theory, and then multiply by 100. We should get a number less than 100%, and so 81.9 makes sense. If we come back here and look, answer A is ridiculous, answer D is ridiculous. So B, C, and E mathematically are possible. These amounts and like the molar masses aren't terribly different from here, and since you started with 50 and 28's a decent, the numbers are about similar to each other while the molar mass is about the same. I wouldn't expect it to be answer B. So if I was taking the test, I'm like, there's no way it's A, there's no way it's D. It's probably not B either. C and E seem like the reasonable ones. So if you were short on time, or you want to just tackle the ones that are easiest, I would, cross a line out through those, underline C and E, and then, save that one to come back, since the problems are all worth the same. 19. This one tells you determining the limiting reactant and the mass of the nitrogen can be formed. So this one just flat out tells you. Then it gives you the molar masses here. So the way you need to do this is figure out how much of any product, doesn't really matter which product. It looks like, and here you picked nitrogen gas, but it doesn't matter. You could have picked the water either. It really doesn't matter. So you need the molar mass of each. So we'll get out of the grams of each one. Then the ratio of each. So N2O4 is in a 1 to 3, N2H4 is in a 2 to 3. Then we don't need to change to the number of moles of N2 because just as long as they're the same. And that's because we're not going to do the percent yield or anything. So 28 grams per mole just gets it back into the amount. You didn't have to actually put it into the grams. You could have just done it in the molar amount, but usually when you do one of these, you're usually doing the percent yield. And, if it's in a lab, you're almost always doing the percent yield. So these numbers, you would need one or the other anyway. But then it's just the one that's smaller. So that tells you which one's limiting. And this is typical in these problems where they want to see if you know how to do it, that they set up and pick one where even though you have more mass of N2O4 than the N2H4, it's not it's the limiting with the larger mass, which is counterintuitive to someone who doesn't know that it's based on molecular weights and then mole to mole ratio from the balanced equation. 20. This looks like one of our ionic equations that we covered last Tuesday. So we've got the equation above here isn't balanced, right? The S here tells us that it's one of those precipitation ones. So that's our product. We've got 3 iron here. So the only way to get 3 iron is then to have a 3 in front over here. So that would make it answer A or E. That would eliminate B, C, and D. All right, then we've got a 2 here for the phosphate. So we need 2 phosphate on the reactant side. This is where the phosphate, the PO4 is coming from. So we need a 2 there. If we look down at our 2 options, A and E, there's a 4 here. And A is correct. Obviously, you can already see, and there's a 2 there. And then we don't really care about, since it's precipitating out, that's what we care about. We don't care about the sodium sulfate. It's still in solution anyway. '21 is a titration. It tells you that it's a titration. The other indication here is the parentheses where it says it's neutralized. Sodium hydroxide and HCl. So they each are, they're combining and again, the uneven splitting of water. So water's H2O. We've got the OH here, the hydrogen, the proton from the HCl is going to combine with the hydroxide from the NaOH. That gives us water. Then we'll just get normal salt water, sodium chloride around. It's in a 1-to-1 ratio. So we know the volume and the molarity of the base. From that, we can find the moles, and we know that that's equal to the moles for the HCl. All right. It looks like the volumes are almost identical, 23.25 and then 21.45. So the concentration is going to be really close to 0.1. This one's a fill in the blank, but if it was a multiple choice, you could eliminate answers. Since the volumes were nearly identical, the concentrations must be very close. And then the sodium hydroxide used a little bit more. And if it used a little bit more than the HCl, that means that the HCl must have been a little bit more concentrated. So I'm looking for an answer that's close to 0.105. It looks like it's going to be off by like 5 or 10%, and it's going to be higher. So you can already see the answer here, but I would expect 0.11 or something close to that. Okay, change the volumes from milliliters to liters just by moving the decimal point. A volume in liters times a molarity gives you just the number of moles, and then divide the number of moles of the sodium hydroxide is the same as the number of moles of the HCl. So then you're dividing by the liters of the HCl, and that gets us to the molarity. And then what's typical in here, but again, I'm not trying to trick anybody, right? This number had 3 sig figs. The volumes had 4, so your answer should technically have 3 sig figs, not 4 sig figs reported. Again, I'm really not trying to trick people with that. And I'll go back and in our class, it's small enough. I can go look at everyone's exam, and if you do make that mistake, I'll give you the point back. But it's just better not to. In some of the classes that I used to do at UH, there's 300 or 400 students, and checking. The whole point of having a program like La Lima is it does the grading for you by hand, so you don't have to go in and grade 300 exams by hand. 22, a naming one. So I did put one acid naming one on there, but again, these are pretty straightforward. Especially you can just flip to the page in the book or the slides and see. So that's sort of busy work, not really a problem. Anyway, the polyatomic ion, the SO3, is sulfite, not sulfate. That's SO4. There's a 2- charge, but it's not written there because we can see that it's an acid. It starts with an H. The ite means it's us, so sulfurous acid. There's definitely 1 or 2 of these dilution ones on here because you can't Google these things. You have to, put it in yourself. And the math is pretty straightforward if you know how to do them. So the dilution equation is M1V1 equals M2V2, and we'll use this same equation when we talk about gases. This is a shortened version of the ideal gas law. Anyway, so 12 molar, this is in the ballpark when you order HCl from a chemical company. It comes really concentrated, and then, in a lab, in a school, usually the people in the stockroom already dilute it for you. But, if you end up working, we're doing upper division, research projects or whatever, if you work in the stockroom, you would be the one diluting something really concentrated like this. Same thing as laundry soap. Okay, so 12.1 molar is needed to create 250 mils at 3.2 molar HCl. So our first molarity is 12.1, and that's the X we're looking for, how much to pour out. Our V2 is 250 mils, and these values, as long as they're the same, right? So when it's the thing you're looking for, we're looking for volume. If we leave milliliters in, that means your answer's in milliliters. So you just want to make note of that the units have to be the same. And whatever unit you leave out, its corresponding partner is what gives you the unit for that. So 250 times 3.2, divide both sides by 12.1. And you can see, right, it went from, roughly 12 to 3. That's 1/4 ballpark. So what's 1/4 of 250, right? 6 times 4 is 240. 6 times 4 is 24. So yeah, something about 60 milliliters makes sense. 24 is another balancing one. This one is this one's tricky. This is more multiple problems in one, kind of. So methane is CH4, told you what it is, reacts with the oxygen air. So remember, oxygen air is O2, not just oxygen, the atom. Produce carbon dioxide and water. So the way this one was written, you needed to know the chemicals and their formulas. Then combustion, you needed to know what that looks like, and then balance it correctly, right? This one's already balanced written in here, and I didn't walk you through the balancing, but right, the carbon's already balanced, so it's the hydrogen, right, and the water. We needed 4, so we needed 2 over here, and then now they're even, right? 2 oxygens from the carbon dioxide and 2 from the water. So this one doesn't need to be multiplied by 2. Okay, then it's saying ammonia, and it gives you the formula for that. Reacts with oxygen again in the air to produce nitrogen monoxide and water. So same thing here, where you got to come up with the chemical equation and then balance it. So with this one, you've got nitrogen and hydrogen, and so you need to do those two. You can do whichever one first, doesn't really matter. The first thing I notice is that there's one nitrogen in the reactant and one in the product. So whatever coefficient's in front here of ammonia, it's going to be the same in front of the NO. So that would make me kind of not in a rush to do the nitrogen, like what difference does it make? I would tackle the hydrogen first. All right, we've got 3 on the reactant side. There's no way to have an odd number. So we need to multiply by 2, obviously, to start with. 2 times 3 is 6. So 3 times 2 is 6. So now we've got 6 hydrogens on each side. When we did that, right, whatever coefficient's in front of the ammonia, it needs to be in front of the NO as well. So that 2 needs to be a 2 here. Okay, now let's do the oxygens. Right? 2 times 1 is 2, and then 3 times 1 is 3, so that's 5, so that's odd. The way you get rid of these odd things with O2, you have to multiply the whole reaction times 2. So that becomes 4, and then what was 5 halves becomes just 5, 4, and then 6. Okay, now that's just the first 2 sentences. Let's go back up and look at what it's actually asking us. What mass of ammonia would produce the same amount of water as 5 grams of methane reacting with excess oxygen? So it's saying 5 grams of methane, it's the limiting reagent, and it's asking us about water indirectly, then back to the ammonia. So first, 5 grams, we want to get into the number of moles. Now we have the number of moles. We want to get into the water. So from the balanced equation up here, the mole to mole ratio, methane to water is 1 to 2. That gets us to the moles, right, from our moles of methane to the moles of water. Now it's saying it wants to know the mass of ammonia. It would have the same amount of water for each reaction. So now the moles of water, we want to convert to the moles of ammonia. So this 0.625 moles of water in our second reaction here. And how are they related? A 6 to 4 ratio. So we want the water on the bottom to get out of the moles of water and then multiply by ammonia on the top. So that's why 4 on top, 6 on bottom. This gets us to the moles of ammonia. And then last periodic table, and I didn't carry a lot of digits here. I'm sure on the periodic table it's like 17.01 something. I just used all these round numbers, 16 up here and 17 here. And so you'll get roughly 7 grams of ammonia. $25. Looks like it's another balancing one. This one's a bit easier. Well, I mean, it's fill in the blank, but it's like the one above. The thing on the product side that has aqueous next to it doesn't go into the ionic, right? Those are all spectators. They're just bouncing around in solution. So it's really only the magnesium hydroxide. We've got a 2 there, right? Because magnesium, it's on the periodic table. In group 2, it's a +2. The hydroxide is uneven splitting of water. It's a -1. So we need 2 hydroxides. That means we need a 2 here in front of the KOH, which really just translates into 2 hydroxides. Right? Everything else is still in solution, so it doesn't need to be there in the net ionic equation. Pretty sure there's a density one, maybe there's 2. which is what 26 is. What's the density of a compound that has a mass of 34.9 grams and a volume of 6.71? This is pretty easy. So this is a good example of a problem that would be on the test that I would expect you could do in 30 seconds to a minute. So for example, right, 24, the problem up here is a bit more lengthy. Like this would, would take me a couple minutes to write it out, balance it. And this one's excessive. So this is a good, example of, a challenging problem. Too long for a test, or maybe two-part, like balancing it would be problem 24, and then, this mass would be problem 25 or something. But this one you could do pretty quick, right? This is just, okay, density is mass over volume. There's the mass. There's no molar mass, or we don't even know what the compound is. We're just dividing the two numbers and then rounding. So a good example here of rounding, right? There's 3 sig figs in both numbers. So your answer should have 3 sig figs. The 1 rounds down, so 5.2. 37, what's this one? This is a molarity one. There's one of these, maybe 2 of these on the test. This is another one that's, takes math. You can't Google it. You have to know how to do it. But the math that you're doing isn't terribly difficult. So go to the periodic table, get the mass of sodium chloride to get out of grams and into moles. Then we're dividing by the volume, but not 150 milliliters, because molarity is moles per liter, so you need to move the decimal point over, which is the same thing as dividing by 1,000, so 0.1050. Then divide the molar amount you found by the properly shifted over liter amount, and then I should delete that. And then we get 0.3926. There's technically 2 sig figs in here, so the answer should have 2 sig figs. So you round the 9 up, and that makes 0.40. Again, I'm not trying to trick anybody by rounding. There'll be a couple like this, fill in the blank, and then there'll be a couple, or there'll be more that are, up here like this, where, there's no numbers close to each other. You're not deciding between 81.83 and 81.93, that type of thing. Okay, let me. So that's all I had prepared technically to do. So I hit the unmute button, or if you want to use the chat box, if there's anything in particular you want me to go over, even redoing or talking one about the ones on the study guide, or anything from PowerPoint, the book, whatever, feel free to do now.
So are we having around 25 problems for our test?
Yeah, there'll be 25 problems. I'll start the Zoom early so we can do some last minute review and stuff like that. I'll start it at like noon. I know some people might have class before. It's annoying on Laulima. Well, they change it from time to time, so I'm not sure exactly how it looks. And of course, I don't know, the student view. Let me pull it up. I know this was a problem. So when everything switched over to online, they weren't used to using it. And so here it'll be in one of these tabs. You just go to it. And if you click on it, I know before, unless they fixed it, as a student, when you clicked on it, nothing would be there, because I would get emails from people like, there's nothing in the test for the quizzes. So just don't freak out because you don't see it thinking like your Laulima is broken or something. It will show up there. And it'll be there at we start at 12:30. It'll be there at 12:35, but I'll be here on the Zoom beforehand, and then I'll email out a PDF version of it, so that there shouldn't be, with PDFs, right? There shouldn't be any formatting issues. You can see it, and then it'll be like a normal test where if you want to print it out and you like working with it by writing out the things and treating it like a normal in-person test. Also, I've had this where there was some sort of car accident in Kailua, and like someone crashed into a pole, and several students that lived over there lost power when that happened because they sent me emails from their phone, right? But their whole house went out. So it'd be good to at least download it as soon as I send it out, so that you have a copy of it. So if you lose power somehow, especially if you're on a laptop, if you have, like even me here, I'm doing this on a desktop. If the power flickers where I'm at, I'll be cut off and I won't be able to get back on until the power comes back in the router, etc. So, and I set the test for 60 minutes. So we'll start at 12:35 and go till 1:35. Any other questions, comments, thoughts, feelings?
So when you say oxygen boils at negative, is that actually a thing?
Yeah. So let me pull back up. Where was that one? Here. Yeah. So the way that they, like, if you are into scuba diving or whatever, one of the ways they separate gases is by just compressing the air we breathe, and you can pump them down and liquefy them. Then as you bring the temperature back up, just like gasoline and other things like that, they separate these things by their boiling points. So it's weird to say boiling point because it as a gas, but you can actually lower the temperature and then separate things by their boiling points. So liquid nitrogen is something you'll probably see if you stay in science related classes. This one's online, but I always bring liquid nitrogen to class. And it's a pretty cool thing to see if you've never seen it before. You can pour it out on the ground and on a hard surface. It's like you've seen boiling water, but it moves like a hockey puck, right? There's no friction because the liquid is protected and floating on a little pocket of gas. So those hovercraft boats where they have like a big sort of balloon like thing that goes around them, and it floats on a cushion of this inflated compressed air. And so that's one of the ways they separate these things out. And that's where, if you've probably seen dry ice, which is not water at all, even though it has the term ice in it, it's carbon dioxide. And so the way they make that is they just take the air that we all breathe and they just compress it. And carbon dioxide, when you compress it down by those phase diagrams, it turns into a solid. So they basically just freeze it out. And that's where you can get these chunks of dry ice if you've seen those. Usually people see those more around, Halloween or something. But in biolabs and organic chemistry labs, they use dry ice, kind of the same way that you might use just ice. If you go to the beach for the day, you buy a bag of ice at the gas station or the grocery store. The dry ice is actually much more useful in the logistics sense in the science world because it evaporates as a gas, and so it doesn't get like if you were going to send a protein sample across the ocean to someone, normal ice turns into a liquid and then it gets wet, right? And if you put it in an envelope or a pack, however you package it, it's just going to get the cardboard and the paper all wet. But carbon dioxide evaporates, sublimes, and turns into a gas, and so you don't have this soggy, wet box or paper and whatnot. So it gets used in that sense. separating oxygen and nitrogen is rather challenging and expensive because their boiling points are similar, right? It's as we'll see when we talked about it a little bit, the formula, right, for oxygen is O2, the formula for nitrogen is N2, and they're right next to each other on the periodic table, and they're both gases. So separating things that are really similar is difficult, and that's one of the reasons oxygen is kind of expensive to buy on its own. It's because you're really trying to separate it away from nitrogen, which there's a lot more of. So 80 to 20, 4-to-1 ratio.
And some of the markings on the periodic table, some of them have like outline like a black letter,
Yeah,
and then some of them are like see-through. You mentioned that earlier.
yeah.
What was the purpose of it?
So the color coded, right, tells you what phase, solid, liquid, gas. Then the solid is something that is naturally occurring in here on Earth. So, not to get into creationism and whatnot, but the solar system, et cetera, planets, everything's pretty widely accepted as a big bang explosion. And all these things that are solid here, they have stable isotopes. The ones that are outlined don't have any stable isotopes. So from 93 on, these things are all made. They were never here on Earth. These other ones, there's actually uranium in the soil. Most of the uranium that we have comes from like New Mexico area. And it's radioactive, but the lifetime is like, half-life is like, a billion years or something. So you can actually measure it out and weigh it and stuff. But these ones with the outline that aren't solid all the way through, they didn't exist on Earth. And so samples of these, and that's where the technetium comes from. This one too, promethium, although I don't know what use it has. The technetium one gets used in a lot of cancer imaging, so that's why it's more relevant. And usually everybody has a family member that's had some kind of cancer, so they might have been exposed to technetium for that imaging technique. And we'll talk a little bit about those techniques later on once we talk about electrons. But yeah, that's what the outline means, which isn't terribly important. It's not important for our upcoming exam, right? The useful stuff from our upcoming exam that you're going to use is just the mass off here. There's the proton number is the number up in the upper left corner. That's the only things we've really, and its location, +1 for group 1, +2 for group 2, etc. on over. So that me mentioning that and putting in there is just explaining a little bit more about this particular periodic table, but it's not going to be directly on the exam. Good question though. Other questions, comments, thoughts, feelings? Crickets, huh? Well, I'm around and not terribly busy, so if you come up with other questions or anything else you want to ask, feel free to email me, and then I'll, if it's something kind of good, or that I think the rest of the class could benefit from, then I'll put it into I'll make a video off Zoom, and maybe a figure or two or whatever, and email it to the whole class.
I do have another question.
Yeah, go ahead.
You finish the test, like maybe the next lecture class afterwards. Will we have time to sort of go over the questions together?
So usually what I do after, like in a normal in-person class, it usually takes a while or at least I'm used to these huge classes where people miss it because car accidents, this or that, or travel, sports teams, whatever. But in these online ones, you know, unless you're like in the hospital or like break your leg, we should all do it all. It should all be done. And then since it's already out there and I email it out, anybody who misses it's going to have to take a completely different test. So next Tuesday, I will go over the answer key and then I'll put the answer key in the Laulima on the resources tab on that folder that said exam material where the study guides were. So you'll have, and on Laulima, you can go back and look at your answers. I think an hour or two after the exam, it'll show you your answer and the right answer. So you'll be able to see before then. I think it gives you your score instantly, but I might have put a delay on there until till everyone's done with the test at like 1:30 or something. So yeah, you'll know how you did really quickly if you want it there. So
Okay, thanks.
yeah. And it happens every now and then. There's like a little wording that seems, I think it's obvious, but you could argue a point, or maybe, on a multiple choice one, if it's a conceptual worded one, you could argue, maybe like answer C would be fine instead of just D. And so I've gone in Laulima, I can go back in and make answer C and D correct. That happens on occasion, and I want it to be fair, obviously. So
Can you quickly re-go over 21,
21, let me put it back up.
the titration?
This one, the titration one.
Yes.
Yeah. So it's a 1-to-1 ratio, which I'm just like picking what I think kind of the pitfalls would be. Since it's 1-to-1, then what we're really doing is from the thing it gave us the most information about, which is the volume and the molarity, that gets us to how much actual sodium hydroxide was added, and those two amounts are equal. All right, then once you know that amount molar wise, then you're just dividing that by the volume. Now, this one was left here as fill in the blank. But my point was that when I was talking about it is that you can see the volumes are almost identical. And since the volumes are almost identical, that means the concentrations are going to be pretty close to one another. So, but then, that's, if it was multiple choice, you can see the answer already here. But since the concentrations are similar and this one's a little bit larger, I'm expecting than this guy, I'm expecting the concentration of the HCl to be a little bit higher. So, if this was multiple choice and there was only one answer that was just above 0.105, and then I would know it would be this, and you wouldn't even need to pick up your calculator. But if it's a fill in the blank, you obviously have to, do the math correctly. So change both of the volumes from milliliters to liters. That's right, just moving the decimal point over. Then molarity is moles per liter. So when you multiply those two, the liters cancel. Now we get to our moles of HCl. I forget if on the test which one I put, but this one is 1-to-1, right? 1 mole of sodium hydroxide to 1 HCl. If it was something like, where's that last one? Magnesium hydroxide down here, right? There's 2 hydroxides. So if it was magnesium hydroxide and HCl, then you would need twice as much HCl. This one was 1-to-1 because sodium hydroxide has 1 hydroxide and HCl just has 1 H plus. So that means the moles of the sodium hydroxide is the same as the moles of the HCl, right? Then just molarity is dividing moles by liters. And the number makes sense, right? It's a little bigger and should be a little more concentrated because we needed a little bit less of it. And these titrations are pretty classic in labs where you're doing analytical stuff and you want, precise things. And you'll do this if you're a bio major in OChem and in and should at some point in 161. I don't know all the details of the 161 at HCC though offhand. That makes sense. That help?
Yeah, thank you.
Question.
Yeah.
So for the most part, it's gonna be bit, other than Googling, the specific grams per mole, like however grams are in that mole of uh, compound, like number 19.
Usually I'll give them to you like this. If it's a fill in the blank one, I want us to all use the same one so that I don't have to go back in and regrade it. And then, when you get it back, if you did it right, you have the right score there and you don't have to be like, hey, Dan, rounding, I used, 92.03 or something and got a little different number. So for the most part, I'm just going to give you these in a normal test. In an in-person one, like you're supposed to show that that the molar mass comes from the periodic table where you go take the mass of two nitrogens and 2 times nitrogen plus 4 times oxygen. But in an in-person test, and we went through this all, when we went forced to go online and started using this, is that it became like this little black war between students and faculty of, and the old guys that I used to teach with tried to stop, it, quote unquote, if you want to call it cheating, but like where they're saying can't use the book, and like how do you know what someone has taped up around the room where you can't see it on the Zoom call? So for us, I want you to be there on Zoom and turn your camera on just so that I see it's you and not like a group of your friends doing right? It's not a group project, it's an individual test. But you could easily just pick up your phone and type into Google N2O4 molar mass and it's going to spit out a number. So in an in-person class, we used to have like an easy question would be, what's the molar mass of N2O4? But in these online ones, it doesn't make any sense to do that when you could have your phone off the view of the camera and just type Google N2O4 molar mass and it pops up. So it makes the type of questions need to be different. And so obviously like 24 here is a lengthy problem. That's, a bit much for if all the problems are worth the same, that this would be worth 1 point, where this density one here, where you're just dividing the two numbers, is worth the same. So there's definitely problems that are, more calculations and take longer. And so on the test, you want to get through the ones that and that are easier for you. And surely, like, even if you're, this number 24, even if you like them and you're good at them, they still take longer than say, number 25 or number 24. So, so there'll be a few like this 24 where, this is how long would you say this problem takes you to do? It's really just, oh, it's density. It's just some random compound. All right, 34.9 divided by just 6.71, 5.2. It's pretty easy to do. You could, like that one, you could be done with that problem in 30 seconds or something and have it, click on if it was multiple choice, click on Laulima on the multiple choice and move on to the next one. So the quicker you get through the easier ones, the more time you leave yourself to do longer ones. Now, there won't be one as long as 24 on the test. This is sort of, 2 to 3-ish problems in one, in my opinion. other questions, thoughts, feelings? Okay. Well, I know it's a minute or two early, but we're basically out of time. So I'll post this as usual. If you think of anything else, as long as it's not, well, even the morning of, I'm not terribly busy Wednesday morning, and I'll log on earlier. I can start the Zoom at 11:30 and be here for last minute questions before the test starts. Then again, it's going to open on Alima at 12:35, and I'll email out a PDF of the test. That'll look pretty similar to the study guide, it's just off a Word doc and etc. But it'll be a PDF instead of actual words, so there's no formatting issues. So shoot me an email if you come up with any other questions between now and then. And if not, then I'll see you Wednesday morning.
See you Wednesday. Have a good rest of your day.
Great.
Thank you,
Thanks.
Dan.
Thank you. Have a great day.
You too.